Okay, guys, welcome to, let's see, close that out. All right, so welcome to another week of database management systems. Today we're going to be discussing normalization. So I had prepared, we had talked about an example that we could do an ER model with. But since we're a little bit, actually, we may be a little bit ahead, depending on what ends up happening next week with Ramazan Baidam and stuff like that, whether or not we'll be meeting both days next week. I haven't been given any information about that yet, so we'll find out what happens. We'll not find out what happens with that. But what I decided was what would be better would be go ahead and finish out this normalization, at least the initial normalization discussion, because you may have noticed that there was an assignment posted for your group project. Let me do this. Let me say that what I want from that is one submission. Okay, don't submit if you're not the group leader. Okay, I will only grade the submission that comes from the group leader. Okay, so if you are not the group leader, you don't have to do anything with it. Okay, as far as the submission, as far as like actually submitting it on Microsoft Teams, you don't have to do anything with that. Only the group leader should be submitting it. In fact, what I might be able to do if I have time for this is I'll set up the assignment to be only assigned to the group leaders. That's a good idea. All right, hold on. Let me make myself a note to do that. Just so that it removes any confusion from you guys. Okay. One other thing. Okay, yeah, the other thing is if you received an email from me today saying that you are not in a group, it means that I never received any email from you or that was CC'd to you that said to include you as part of a group. Also, I never received any request from you to reuse a previous project grade from a previous year. So as far as I know, you are not reusing your old project grade and you are not going to be doing a project this semester either, which would mean I have to record a 0 for you for the group project, which if you look at the syllabus is 30% of your grade. So quite a bit. So you have until the end of the day today to contact me if there is something wrong with that. If you have evidence that you are supposed to be part of a group, then you need to contact me so we can get that straightened out. Okay. Let's see what else. I think that's it. Okay. Actually, I'll do this during the second hour. I want to go ahead and get into the slides. So let me go ahead and get up to that. So during the second hour, we'll talk about the group project a little bit more so that you guys can understand what the first submission should look like. All right. Okay, let's talk normalization. Well, first, quote of the day. If you know who Maya Angelou is, she's a famous poet. She read a poem at, was it Bill Clinton's inauguration? I think it was Bill Clinton's inauguration. I think that might be the first time I remember seeing her. She wrote a poem called I Know Why the Caged Bird Sings. Pretty famous poet, but she brings to us our quote today that if you're always trying to be normal, you will never know how amazing you can be. If you just try to go with the status quo, if you just try to be bare minimum, then you won't accomplish great things. People who accomplish great things are not people who just try to do the bare minimum amount of work, right? They're trying to figure out, how can it be better? How can it be better than just normal? Okay. Another quote, I can't remember who said it right now, but Another quote I know I've run across is some of the worst words in engineering are, "This is how we've always done it." We don't like to think about how we've always done it. We want to think, how can we do it better? Okay. All right. So, but as far as normal is concerned, we do want to normalize our database, which is all about reducing data redundancy and reducing what's called update anomalies, and we'll talk about both of those terms today. Okay. One of the terms that you'll need to become familiar with is this concept of a functional dependency, which is how different attributes within a table or within a relation are related to each other. Okay. We're going to determine how to identify functional dependencies. All right, we can also use functional dependencies to identify what the primary key or a candidate key of a relation is. This particular set of slides, we will talk through the first normal form, well, the unnormalized UNF, which isn't listed here, but we'll get there. First normal form, second normal form, and third normal form. If you've looked at the assignment for the group project, you will see that the third normal form is the highest that I am requiring for your database for this group project. One of the things you'll discover when we talk later in the more advanced normalization set of slides is that for most of your group project style databases, once you get to the third normal form, you've pretty much already gotten to the higher levels also. That I don't expect that many of you will have data sets that are so robust, so complex, so have so many of these other different types of issues and dependencies that that you would have to go through the process of getting them into the higher forms. So because what we'll discover is that any database that is in third normal form is also in second normal form, and any database that's in second normal form is in first normal form. And so we'll talk about why that is. We'll talk about how that is when we get there. Okay, so moving on. Now, one of the things that I want to make sure we understand is, let's see, normalization. What we're trying to do is we're trying to reduce, again, data redundancy. That's on a different slide. Okay, but reducing data redundancy, right? And we're trying to also make things easier for our database management system to access the data and to maintain the data, make it easier on the DBMS to do that, and taking up the minimal storage space on the server as well. One of the things that you may hear me say a few times here is that things that seem easy to us can be more difficult for the computer or for the DBMS. Things that may seem more strange and difficult for us actually can be easier for the database to maintain. So I will show you some examples of that, of why that's the case. So where we might keep the same data all in one spreadsheet, for example, we might say it makes the most sense to us that if I'm looking for, let's say I was wanting to see a list of all students in our department and all the courses that they are taking. Now, it might be easiest to just have that all in a spreadsheet, right? One spreadsheet, one table in the spreadsheet, or one tab in a spreadsheet. And what you would have is you would have all the student information, and you would have all the course information, and you would see like just a list of all of them, right? and so your name would appear multiple times for every course that you're taking. The same course would appear multiple times once for every student that's taking it, right? And so that might be the easiest way for us to look at the data, but actually that format, storing the data in that way for the DBMS, can cause a lot of problems. That's a lot of data redundancy that's unnecessary. That's also a lot of potential for, again, what we call update anomalies, which is where what if we update or change a value in one place, but it doesn't change in the other? That can cause a problem. Okay. One of the things I was going to say about normalization is that normalization is a process. It is a systematic process. So we're not just taking every table as it comes and saying, oh, how would this look better, or how would this be able to be reduced? There is a specific process that we're going to follow to be able to normalize any table that is in our database. All right. Okay, let's see. Visual. So this is basically how normalization supports the database design. What we can do is, once we have our data set, our database normalized, we can use the normalized tables to generate our ER diagram from it. So we talked about ER diagrams last week. We can take an ER model and produce tables from that. We can also take an existing set of tables and produce an ER model from that. There's no one way that's right in that. We can go both ways. We can, and they can kind of work with each other too. So we may start with an unnormalized data set and normalize it and end up with some tables, and then bring that into an ER model. And then we might modify that ER model maybe as updates come along, or as requirements change, or even if we find something in the ER model that is not quite correct in our design, and we could change the ER model, which would then change our database, which we would then change our tables, right? So it can kind of go both ways. We change the tables, it changes the ER model. We change the ER model, it changes the tables, right? It can go both ways. Okay. All right, so I've mentioned this a few times already, this concept of data redundancy and update anomalies. So here, if we want to group attributes into relations so that we minimize data redundancy, meaning that if a particular piece of information is the same every time another piece of information is true, then we only need to store it one time. We don't need to store it multiple times. That it has to do with data redundancy. And the truth is that I think, especially as data storage has become so huge, and there's so much access to data storage space, we probably don't think about, as programmers, as users, we don't necessarily think about minimizing our data redundancy as much as we probably should. But it is an important concept, and especially if you ever work in big data topics and research, you'll definitely want to minimize data redundancy. And even from just another aspect of it is that if there's a lot of redundant data, it can cause slowdowns in searching for data as well. You know, I mean, the truth is, my wife, for example, like, she'll get messages all the time about she's filled up her Google Drive, and she needs to go through and delete them. And then a lot of times it's because she's got the same document stored in multiple different places, and she just, I forgot where I stored it last time, so I just did a new one, right, or something like that. And so I tend not to do that kind of stuff, but but that's an example of a data redundancy that's unnecessary. But because I'm given access to gigabytes and gigabytes of data, then why do I need to be worried about data redundancy? I think can be an issue that we've run into. The other thing, the minimal the data inconsistencies that has to do with data update anomalies. So the idea being here, what happens if the data is changed in one place, but it should be changed in more than one? And if it's not, then we can have conflicting information, which could cause problems. All right, so maybe an example might help you understand this a little bit better. Okay, questions or comments, good. Okay. All right, so let's imagine that this is how you might see data stored like in an Excel spreadsheet or something. So we're wanting to know, our staff people, right? And what branch they work at and what address that branch is. Okay. So we would look at it something like this, and this would make sense to us. The way this would be stored in a database, though, in a normalized database, would be across two separate tables. Now, this is a simple example that could show how the storage in the database is easier for the database to understand that, but as a human, we might have a harder time with this. Consider this. If I wanted to say, I want to send a letter to John White. I want to send a letter, which I know no one sends post, one uses the PTT for sending letters anymore, I know. But let's say that you did. You want to send a letter to John White. So you need to know his address. All right. Now, if I were to have a set of spreadsheets where I said, okay, the first thing you need to do is you need to look up John White. You need to look at his branch number. Then you need to go to the branch spreadsheet tab, and you need to match that branch number with this branch number, and then you can learn the address, right? Okay. Now you would say, okay, well, that's not very, very difficult, but it is an extra step, right? I have to look at his branch number, then I have to go over to the branch tab, and I need to look at that address, right? You say that's an extra step. Whereas if I stored it like this and I said, okay, find John White. Oh, look, his address is just there. It's where I'm already looking. Right? So this is an example where if we were as humans storing this information, it would look, we would probably store it in a spreadsheet like this, where all the information is there on the same sheet, so that I can see it quickly, I can find out that information quickly, and I can be done. Right? But here's the problem. Notice that B005 shows up twice. Right? B003, where's my mouse? Okay, B003 shows up a few times. Right? Okay. So what happens if, and let's see, who's the manager of B003? Susan Brand. Okay. Susan Brand calls us to a meeting and says, okay, so B003, so our branch here at Main Street is, the rent is too high. We all know, right? Rent can go very high in places, right? All right, so rent's too high, we need to move. and we need to move. We're going to stay in Glasgow, but instead of being at Main Street, we're going to move to a different address, okay? So Susan, we go in and we change her address to, let's just make a simple change to 263 Main Street. Okay, so we changed it for Susan because she was the one that called the meeting and we announced it, and now her address is changed in there. Okay. So now everybody at B003 now works at 263 Main Street because we went in there and changed it. But we only changed it for Susan. What if I send a letter to Ann Beach at 163 Main Street? Will she get it? If I send a letter to Ann Beach at 163 Main Street, she won't get it because she's not working at 163 Main Street anymore, right? She's working at B003, which is at 263 Main Street. Right? This is an example of an update anomaly, right? Where we changed it for one row for B003, but we forgot to change it for the others. Right? So in this format, by separating it out into two tables, a staff table and a branch table, if Susan calls a meeting and says, okay, hey, branch B003, we're moving. Rent's too high. We can't afford it anymore. We're moving to 263. If I change it here, right, then what happens? Now I want to send a letter to Ann Beach. My database looks at B003, goes to the branch table, says, hey, where's B003? It's 263 Main Street. Now I send my letter to 263 Main Street. Does Ann get my letter if I send it to 263 Main Street? Yep, that's right. She does. Okay. Also notice that in this format, even if there isn't any data inconsistency, even if all the data is consistent, that's still 1, 2, 3 times that I'm storing the same information over and over again. I don't really need to have the same information stored that many times, right? And so here we only store it one time. Okay, now in this simple example, it might seem, that seems like a bunch of overkill. Like, this doesn't seem like, and for a small set like this, yeah, it can seem that way. But when you start talking about thousands of rows, millions of rows, you start talking about large systems, huge systems like Amazon and Google and Hepsiburada and guys like that. Having this stuff normalized becomes hugely important, extremely important. Okay, so that's just an example of an update anomaly and a data redundancy issue where, again, we'll mark this the human way and the computer way. So this is easily understood by a human, much more easily understood and maintained by a computer is the top one, which also comes back to why we would then create views. Because what we would do then is we would store it like in the top version here for the computer to use, but then we would create a human readable view that would show them the information like this. Okay. All right. Moving on. All right. Okay, so this just kind of describes the data redundancy and update anomalies from the previous slide that we talked about. Okay, some redundant information, update anomalies, and not just modification, but also insertion. What if a new employee comes to work at B003 and we accidentally fill in their address under this old format? A new employee comes to work, we add them to a branch, but when we fill in their address, we type the address wrong. Okay, we type it as for B007, 16 something else street. Right? We accidentally typed the wrong address. Now we've got a problem. We've got inconsistency in information. B007 has some other address. B007 also has Argyle. Right? So that can be another type of update anomaly that can occur. Okay. Let's see. So let's talk about functional dependencies. Okay. And then we'll introduce functional dependencies, and then I think that will be enough for our first hour, and we will take a short break because that's going to be quite a bit for you guys to take in. All right. So the idea is where one piece of information is dependent on another piece of information. Okay. So the way that we would say is that if A determines B, then we would draw it like this, okay, with this A arrow towards B. So, all right, so all right. So there's a few different ways that we can read this. We can say A determines B. We can also say B is functionally dependent on A, or B is dependent on A. We would say that A is the determinant of this relationship. B is the value determined. Okay, there's a special word called determinant. Again, determinant would be one of those fancy words I do not expect you guys to memorize. Right? It's not a bad word to know, but I don't expect you to memorize determinant. Right? So the left-hand side of the arrow, so this is where I meant to draw that whole A is arrow, B is so you guys can know. Okay, so again, what we would say is A determines B. B is functionally dependent on A. You could also say B is dependent on A. Again, if you want to get into the fancy language, A is the determinant of this functional dependency. B is the determined value. Okay. In a sense, it's kind of like if you know much about scientific experimentation, it's kind of like variables where you have an independent variable and a dependent variable. That is kind of how this could be viewed. Right? But the idea is that B is dependent on A. The idea is that if we know the value of A, we can immediately know the value of B. Sometimes this relationship is what we call bidirectional, meaning that sometimes it works both ways. Okay. Let me say sometimes. But not always. Sometimes, but not always. B determines A. Okay. But again, not always. We need to be cautious to make sure that we know which one is the determinant and which one is functionally dependent on the determinant. Okay. So let's look at an example where we have a one-way functional dependency. Okay. In our staff table, staff number determines position. If I know the staff number of our staff person, I then also will know that their position title, right? SL21 is a manager. Okay. But the position does not determine staff number. Staff number is not dependent on position. If I know the position, I don't necessarily know the staff number. Okay. that clear? Is there anybody that's confused by what we've said here? That manager, if I know manager, if I said, okay, I'm going to look at manager, first column says manager. I know therefore that it must be this person. Right? So let's say, for example, here at this university, if I know the employee number of, let's say it's Meli Hoja's employee number, I can say, okay, that's a Bolum Bashkanan, right? That's a chair of a department. But if I say, I need to know the employee number of this person, it's a chair of a department at the university, I don't automatically know what, I don't automatically know which employee number I'm talking about, right? Okay. All right, quick question. So if I had a column, if I had a few columns, let's see, let's say name, we'll call that column A, just use A. Okay, surname. We'll call that column B. And let's say student ID. We'll call that column C in a table. So I have a student table, it has a student ID, it has a name, it has a surname, okay? Using this arrow notation that we've talked about, so this, what we've talked about before, right? Where column determines column. Give me an example. Let's say C determines both A and B, Kershad says. Yep, right. C determines A, doesn't it? If I know your student ID, can I figure out your student name from that? Absolutely. If I know your student ID, can I figure out your surname? Yep. Does it work the other way around? If I know your name, can I figure out your student ID? Right, no, because there's, I mean, I don't know about Abdurrahman Kurshad. There might be only one of you, right? But Umut, Buse, right? Your names are a little bit more common, I would imagine. And so, right, there's probably more than one Umut at this university. There's probably more than one Buse at this university, right? And so therefore, no, definitely, right? As far as surname, same thing, right? There's probably, I would imagine, more than one Choban, Ozkan, probably more than one Ozkan, right? And so no, those, we would not be able to figure out which student ID it is based solely on the name or the surname. And probably might not be able to even based on the combination of those two. Right, which gets us into the next part real quick, is this idea of the functional dependency that holds for all time. Okay, we need to be careful about anything that looks like a functional dependency that's now true, but might not be true for all time. Okay? So if we look back at, now this says slide 7, but it's actually because of the quote of the day thing, it'll be slide 8, right? But if we look back at 8, right? Okay. But when I take the quote of the day out and save it to the drive, it'll be back to 7. All right. We look back at slide 8 here. If we look at, say, the staff number, staff name relationship here, right? What we will see is what looks like a bidirectional functional dependency. Because if I know the name, I know the staff number. If I know the staff number, I know the name. Because in our existing data, staff numbers are all unique, staff names are all unique also, and because of that, it seems that we have this bidirectional functional dependency going. But can we guarantee that this will stay true for all time? Can I guarantee that John White will always refer to staff number SL21? Or is it possible that another John White could be hired and join our organization? So it's tempting to think that staff number determines name and staff name determines staff number, right? But the truth is, the more likely functional dependency that remains for all time is going to be that staff number determines name. This is going to be very important as we start talking about using these functional dependencies to determine a primary key, because things that are on this side of our functional dependencies on the left side will become our primary key, our candidate key, and then our primary key. So if we were to say, okay, this is our functional dependency, name might be part of a primary key, or might be the primary key itself, or a chance of it being a primary key if we did that. But as I've said before, and I've talked with you guys before about in this university system, for example, your name is not your primary key for the student table, or at least it shouldn't be. Again, I don't have direct access to the database here, so I don't know how it's designed, but I would imagine that your name, your surname, is not part of the primary key of the student table. Your student ID is your primary key for your student table. Okay. All right. So we've introduced functional dependencies. We've talked a bit about normalization and some of the purposes for it. It's a little bit early on the break time, but let's go ahead and take the break now. We will come back at about 2:25. And we will continue on talking about functional dependencies. Well, the first thing we'll talk about is a little bit about the group project. Then we will continue on our discussion about functional dependencies. Unless, let me check, are there questions or comments before moving to the break? I do not see one. So, okay. So let's break briefly and we will come back at 2:25.